Astrophysics virtual seminar. The capabilities for Zoom for the university are doing well. The status page says we are fully operational, so if you have any connection problems, it's probably your own internet, so please turn off your video. Today, I think everyone who's joining us is actually just from Chalmers. There's no external people today. The procedure will be the same as previously. If you wish to raise your hand, you can use the raise your hand button. You can also unmute your audio if you want to interrupt the speaker, but it might be better to save your questions to the end, depending on how urgent the question is. Myself and Per will be moderating the session, and hopefully we are recording the seminar, but if there's any objections to this, let me know by email, and we can always cut out any questions you ask if you're not happy them being in the video at the end. So today's seminar is given by Mathilde Jauzac, who completed her PhD at Marseille, did postdocs in South Africa and Durham, and is now an assistant professor at Durham University. Mathilde, do you want to take it away?
Yeah, okay. Good morning, everyone. Thanks a lot for the invitation. First of all, this is my first virtual seminar, so you might see my hands like this, and I'm sorry because I'm not used to that. But yeah, so today I'm going to talk to you about the Buffalo Survey, which is an HST large program that Charles Steinhardt at Durham and myself are leading at the moment. And some of basically what you can do with cosmic beasts. So I know some of you are working on AGNs, and I was reading an article yesterday about those, calling them cosmic beasts, but it's slightly different beasts because those are really massive galaxy clusters. So you can see on my slide a list of people. So Charles obviously is one of my main collaborator, but a few others that need to be highlighted, and you might see some pictures along the talk. One main one is Anna Niemiec, who is at the moment a Buffalo postdoc in the US at the University of Michigan, and she's going to join Durham in May, well, if she can. And then Mathieu Scheller in Leiden, Anna Sebron in Israel, and Guillaume Malin at Michigan, who is also joining Durham. It seems I'm emptying the University of Michigan astronomy department this year. But yeah, anyway, so some outlines. So I'm going to give you a brief introduction to lensing. Apologies for the people that already saw those slides. I think about Jan, Bitten, and Flora mainly. And then I'll introduce the survey and talk about what I specifically like to do with those cosmic beasts, and finally conclude and give you some perspectives. So this slide is presenting basically the cosmological context. So what are we looking at in terms of scales? So this is a snapshot taken from the Millennium 2 simulation. So this is the large scale dark matter distribution. You can see that dark matter is accreting along those what we call large scale filaments. And at the intersections of those filaments, you're going to find the largest overdensities that we can observe in our universe that we call nodes of the cosmic webs, but in terms of astronomical objects, those are the most massive galaxy clusters. So those are basically the cosmic beasts I was mentioning earlier. So in order to study those, I'm going to use gravitational lensing. So gravitational lensing is based on the hypothesis that an important mass density is going to locally deform the space-time. So it has it's a pure geometrical effect, which has no dependence at all on the dynamical state of your object. And if you look at the optical bench that you can see on the left of the slide, we are here as an observer. Then you're looking at a distant galaxy or distant object. If there is nothing between us and this galaxy, you're going to observe it intrinsically and intrinsically fainter as it's further and further away from us. However, if you put something in between us and this galaxy, then the light rays are going to be deviated and magnified. You can see this picture with two really famous men, so Einstein on the left and Eddington on the right hand side, sitting on a bench in Cambridge in 1919. And this picture is because there is some history behind this, Eddington being the first one observationally confirming GR thanks to actually lensing. So the story is basically on 29th of May 1919, there was a total solar eclipse happening in front of a bright constellation of stars. And so that was quite ideal to demonstrate the lensing effect and GR. So in February, January and February of the same year, Eddington measured the true position of the stars from Oxford. And to ensure against bad weather, as a good astronomer, he sent two teams, one in Brazil, you can see that on the left-hand side, in Sobral, and one in Principe, which is a small African island on the western coast of the African continent. Eddington was part of the African team. And during the 5 minutes of totality, they were actually really lucky because both teams got ideal conditions and nice weather. So they got two sets of measurements. In November 1919, Eddington published his results. So from Newtonian theory, you also expect a deviation of light thanks to an intervening mass. However, the shift between the true and the observed position of stars during this lensing effect is actually different from GR and Newtonian gravity. And the shift measured by Eddington was actually in agreement with GR. So that was the first observational confirmation of Einstein's theory, and that was done through gravitational lensing. So now if we go back to our optical bench, why is gravitational lensing interesting in our case? It's because if you remember this distant galaxy that you observe, you're going to observe it distorted and magnified within the lens plane. So this object that is between the observer, so us, and this galaxy is going to appear at an angular position alpha. And that alpha is actually equal to a cosmological distance ratio, which is the distance between the lens and that galaxy and us and that galaxy times the gravitational potential of the lens. And what is actually, in our case, the most important is that this gravitational potential is directly proportional to the total mass of the lens, meaning the total mass, meaning everything. So that includes both the stars, the gas, the dark matter, because if you remember what I said, it's purely geometrical. And in my case, the lens is going to be a massive galaxy cluster. So in the case of a cluster, you're going to observe mainly two lensing regimes. So in the inner core, if you look at the small animation, you can see in the inner core, when the density is the highest, the deformations are going to be the largest. So this is the strong lensing regime. You're going to observe those gravitational arcs, even multiple images of the same galaxy that lies behind the cluster. And as you're going further away from the cluster core, the density is going to drop. The distortions are going to be smaller and smaller. You're going to enter the weak lensing regime. While the strong lensing is usually visible on your observations, weak lensing is not. So you're going to need a statistical analysis in order to extract the lensing signal in the weak lensing regime. But I'm going to go back to it in a few slides. So we go back to a bit of history about strong lensing. So the first giant arc was actually discovered in 1987 in Hubble 370, which is a really well-known, obviously massive galaxy cluster. You can see the image the observers had at the time. So this is a ground-based image from the CFHT taken in 1985. And I don't know if you can see, can you see the, no, you can't see the mouse. But basically at the bottom of this image, you can see this extended curved feature. And this is actually the arc. A lot of people had looked at this image before Sukai et al. And they actually thought that it might have been some issues, instrumental issues. And but Sukai et al. Decided to go for a spectroscopy. And in 1988, they published the first spectrum of this arc and confirmed the redshift at 0.725, while the cluster is at a redshift of 0.375. And so they basically confirmed the gravitational lensing explanation. However, one thing to keep in mind is that they were extremely lucky because most of the lensing features are actually not like extremely bright extended arcs like this one. You have a few, you might have seen many of them thanks to NASA, ESA press releases. But when you're doing lensing, actually what you have to deal with most of the time are actually extremely faint, few pixels point sources. And so one thing that revolutionized gravitational lensing in clusters is actually the launch of the Hubble Space Telescope in the 90s. So if you look at the new image on the right-hand side, this is the exact same field of view, but taken with WIFPIC 2 on board Hubble in 1996. And you can clearly see this beautiful extended arc at the bottom of the image. So this is the object that Sukai et al. Observed back at the end of the 80s. But you can also see many other lensing features. If you look at the top, you can see like distorted arcs at the top right corner of the WIFPIC 2 images, which are completely invisible on the CFHT image. And like I said earlier, the lensing is going to give you a total mass of your object within a given aperture, and this aperture is defined by the distance of where you're going to see those gravitational arcs or multiple images, for example. But you can do many other things. So you can obviously study dark matter because you can observe directly the stars. You can observe directly the gas, depending on the wavelengths you have observations of your object at. And from lensing, you have the total mass. So you do a simple subtraction, and then you recover the dark matter distribution. So this is one thing that I'm going to mainly focus on today. But also, you have the fact, if you remember what I said, lensing is magnifying the light emitted by the background object. So basically, your lens behaves as a gravitational telescope. So you can take advantage of this natural effect to actually observe distant objects that you wouldn't be able to see without the lensing. So a lot of people, and I'm going to also talk a little bit about that, are using this to actually study the high redshift universe. And another point amongst the many things that you can do with lensing is actually you can also constrain cosmological parameters by doing what we call cosmography. So different galaxies are being lensed by a cluster. So you have different galaxies at different redshift behind the cluster. So you can sample the redshift space behind your cluster, and then you can try to constrain your cosmological parameters. But I'm not going to talk about that today, but feel free to ask me any questions at the end of the talk. And now I move on to the weak lensing. So I was telling you that weak lensing needs to be studied statistically, but the theory is actually much simpler. So it's basically that what you're going to observe are those faint blue background galaxy, background by meaning behind the cluster, and the ellipticity is going to be slightly distorted by the lensing effect. So what you're going to clearly observe, the form of your galaxy, the ellipticity of your image is going to be equal to the ellipticity of your source plus the lensing term, which is purely gravitational. And so this term is gamma over 1 minus kappa, where gamma is what we call the shear and kappa is the convergence. And if you look at this, the little cartoon that is on the slide, basically the convergence is if your galaxy is purely circular, we imagine an ideal case, we apply some lensing, so convergence is going to increase the size of your galaxy, and the shear is going to stretch it in one direction and reduce the size in the other. So basically from a purely circular galaxy, you're going to end up with a nice elliptical galaxy. But that's the theory. In practice, like I said, it's not that easy because weak lensing is extremely weak. And if you look at this simulation on the slide, so on the left-hand side, you have cluster with the distortion simulated. So you can see at the bottom left, this is the cluster inner core. You can see the distortions are much larger than in the rest of the field. And then you have the small rectangle at the top right. And if we zoom in, we can see all of those galaxies, and they seem to have randomly oriented. They seem to be randomly oriented. However, if you average over this patch of the sky, you can see that they have a preferred direction that actually follows that is tracing the gravitational potential of your lens. So if we go back to what we really do as observers when we do weak lensing, it's basically we detect all of those background sources, and we're gonna average over a different part of the sky in order to extract the signal. So the initial equation that I showed, so the ellipticity of the image, which is equal to the ellipticity of the source plus the gravitational lensing term, if you average over a number of n galaxy, you assume that all the orientation of your sources in the source plane is intrinsically random. So that term goes to 0. And basically what you assume is what you observe is literally on average the shear signal, which you can relate to the total mass. So now I'm done with explaining basically the tools that I'm gonna mainly use in my in everything that I'm gonna present today. However, you're gonna see that cartoon on all of my slides, or most of my slides, and this is because I'm gonna talk about different scales today. So you have the strong lensing. So this is the inner core of the cluster, really, where the distortions are the largest. And then you have the direct, what I call the direct outskirts of clusters. This is the weak lensing regime. And then we're gonna even go further away, the extended outskirts, so further away from what we call the virial radius, which is basically the physical definition of the cluster. And one thing to keep in mind is that no matter how much lensing is important, lensing is just a tool in order to do science. And you can't do much with just lensing. You actually need observations at at different wavelengths. And without the combination of that, it's extremely difficult to do any science. And everything that I'm gonna show you today is not feasible without the combination of the two. So the Buffalo survey, in order to talk about the Buffalo survey, I have to first introduce what we call the Hubble Frontier Fields. So what are those? They're 6 really massive clusters that have the deepest HST observations to date. So the idea behind the Frontier Fields, it's an initiative that started in 2013. And that was done on the director discretionary time of the Hubble Space Telescope. And there were 840 orbits of HST. And they were wondering what to do with those. So the director at the time, Matt Montaigne, asked a few experts from different fields. And the funny story about that is that he didn't ask them to come. He asked them to send their postdocs to limit the ego discussions. And they all went together, discussed what kind of science they could do, and actually cluster lensing won the battle that one day. And so the idea was to go for extremely deep observations of the core of 6 really massive clusters. And if you remember what I said earlier about magnification, to use those as cosmological telescopes. So in order to observe the really high redshift universe, because if you go extremely deep, you go to extremely faint magnitudes, you add the lensing effect, so you expect to detect those high redshift galaxy. When I talk to you about high redshift galaxy, in that case, up to redshift 10. So, however, it's not the only thing that you could do. You can do cluster physics, you can do galaxy evolution with extremely deep observations. We have, with the Frontier Fields, we had 7 filters, so 3 in the optical and 4 in the near infrared. So that gives you quite a broad range of observations, and then allowing quite a lot of science cases. But to give you a visible idea of what the frontier fields did in terms of lensing features, so if you remember what I said, most of lensing features are actually not bright extended arcs. They're extremely faint point sources. So this image is showing you Able 2744. This is one of the 6 cluster. And the small orange circles are highlighting the strong lensing images that we knew of before the start of the frontier fields. So this was done with like standard depth HST observations. So we had a few in the south and just like a handful of them in the north. And after the frontier fields, we ended up with almost 200 multiple images. You can see the cyan circles are the new multiple images identified thanks to those observations. So we multiply by a factor of almost 4 the number of known multiple images in this cluster. And what is extremely important if you go from one to the other is the fact that before the frontier fields, we only had constraints in the south and a little bit in the north, meaning that while you can constrain the mass distribution of the cluster just with that, even with less, a lot of it was an extrapolation. However, from the frontier fields, now we have almost a uniform distribution of the multiple images, meaning that our mass distribution is extremely well constrained in the cluster core because we have constraints locally almost in every region. And then comes the Buffalo survey. So this is something, so the acronym comes from, means Beyond Ultra-Deep Frontier Fields and Legacy Observations. I have to admit that I have to assume this acronym, but I'm not behind it. But in any case, so we got this program accepted back to 2 years ago. And so the idea is to spatially extend the coverage with Hubble of those 6 clusters observed with the frontier fields. So if you look at the image on the left-hand side, you can see the different pointings that we're going to get with Buffalo. With at the center of each field is the frontier field field of view. So the idea behind it was, again, to go for the high redshift universe and the study of those extremely high redshift galaxies, because by extending the field of view, you're gonna detect more of them, and you're gonna better constrain your mass distribution in your mass model, but I'll come back to this. And also, when you're a cluster person like I am, in terms of cluster evolution, it's actually amazing because you have the high redshift, the high resolution from the Hubble, meaning your weak lensing analysis is going to be even better because you're not covering just the core anymore, but you're going up to, if you remember my small cartoon, up to almost the virial radius of your cluster. The idea also was to get a larger number of high redshift candidates for JWST follow-up, but I'll come back to it later on. So it's 101 orbit. We don't have the 7 filters we had for the frontier fields, but we've still been spoiled, I think. So we have 2 optical filters and 3 in the near infrared. So before we do any science that we want to do with Buffalo, apart maybe from the galaxy evolution in clusters, you have to do a mass model using your lensing constraints. And this is necessary because if you don't know the mass distribution, then you can't get any of the indirect measurements implying the magnification. So with the frontier fields, there was this mass modeling challenge. So they asked all the lensing teams, all teams in lensing are using different algorithms, and they all asked us to provide mass models for all of the clusters. All of those mass models are actually online to allow non-lensing experts to actually use those observations to do their own science. So with Buffalo, we're keeping the same philosophy, but by providing all the mass models from all the different lensing teams that joined the collaboration. So those mass models are going to be online one after the other for each clusters. The first clusters will be released by the summer if everything goes well, and it's able 370. But the difference with Buffalo is because we have this extended field of view, we not just have the strong lensing like in the frontier fields, but we can add the weak lensing. So what you can see at the bottom of the slide are three different examples of what you can do with lensing. So here on the left-hand side, you can see those contours. Those are the mass contours of the distribution in Able 2744, the cluster I showed you before. You can look at the surface mass density as a function of radius, and you can then try to constrain the dark matter slope, or you get magnification maps, and those are extremely important if you're looking at the lens objects, so the objects behind the cluster. I'll quickly talk about some work that Anna and Niemiec has been doing, and we've been working on that for the past year and a half. And the paper was finally accepted as actually a lensing algorithm, which is an evolution of an already existing mass modeling tool, which is called Lens Tool, and this one is Hybrid Lens Tool. Which is now properly combining the optimization of strong and weak lensing. So that might not be say much to you if you're not doing lensing mass modeling, but this is extremely important and not that straightforward to actually combine the two regimes, because one is nonlinear, the strong lensing, and one is linear, which is the weak lensing. So getting an algorithm to do a simultaneous optimization was not that easy, but Anna managed to put that together, and you can see some of her results on a simulated cluster. So you can see on the left-hand side, it's the input with the mass distribution. So it's a really complex cluster. You have the C1, C2, which is the core, and then you have like all of those subclusters that are basically on their way or have merged already with the initial cluster. And then you can, in the middle row, you can see the results from what we used to do, which is basically we used to model first the core and then fix it and then add the weak lensing and the joint fit. The joint fit is when you do the strong and the weak lensing all together. While visually on the mass maps, it's not that obvious that there is a strong improvement. However, if you look at the density, surface mass density of the cluster as a function of the radius, you have the input in black, and you can see that the sequential fit in blue tended to overestimate the mass distribution before, while now with the new method, we're actually matching really well and nicely the input mass distribution. So now that you have your mass model, you can start to do some science. So the main goal of Buffalo was, again, to look at this high redshift universe. So basically try to constrain the end of reionization. So this period between the universe being dark to fully ionized. And so redshift 8 and 10 is basically the period we're trying to look at. The Buffalo coverage in terms of spatial coverage was designed to follow the deep Spitzer coverage we had for all of those clusters. So more than 50 hours per pixel at both 3.6 and 4.5 micron. While Spitzer gives you the age and the stellar mass of the galaxies, the HST will give you the photometric dropout. So if you combine Spitzer and HST, you actually can confirm the redshift, the high redshift of your candidates, and remove all of this like lower redshift below 3 contaminants. You can see on the right-hand side at the bottom the predictions for the number of high redshift galaxies that we expect as a function of the magnitude. But basically, today we have around 25 galaxies, known galaxies at redshift 8, between redshift 8 and 10. And with Buffalo, we expect to detect at least 10 of those within the 6 fields. So here are some examples of some high redshift objects that were detected before. So you have a redshift 11 one that is triply imaged by a cluster, MAX 0647. You have another one at redshift 9 which is a singly imaged in this case, and another at redshift 10 at enable 2744, the same cluster that I was telling you about before. But this is not the only thing you can do. You can also look at the cluster itself as a physical object, and because they're the most massive object that we can observe, they lie at the top of the food chain. And by constraining the evolution, you can also try to constrain dark matter. So by combining strong and weak lensing, you actually can get the total mass of the cluster, because strong lensing is just the core. Weak lensing, you're getting to up to the virial radius and even further. So by combining both, you can know the mass distribution in the whole cluster. One way to actually use the mass distribution in clusters as a dark matter probe is, because those clusters are constantly growing, because they're lying at this intersection of this large-scale filaments, so they constantly have materials falling in. So smaller groups, smaller clusters, galaxies, surrounding material. By thanks to the lensing, you can identify those different substructures, and different dark matter theories are going to predict different number of substructures and with different weight. So by counting and weighting those substructures and comparing those with predictions from numerical simulations using different dark matter candidate, you can actually hope to constrain dark matter itself. But this is not the only thing. I kept on saying that you need lensing, but you need those multi-wavelength observations. But in order to confirm those substructures and make sure they're part of the cluster, and in order to understand the history of your cluster, basically, you're going to need to go to multi-wavelength observations. So you combine lensing with optical, near-infrared, X-ray observations, and you can look at the stars, you can look at the gas distribution, you can look at the kinematics of your cluster galaxies, and try to understand what's happening in your cluster itself. So here is a small cartoon explaining what's happening actually in the cluster that you can see on the left-hand side. So C1 and C2 are two clusters merging in the core, so you're in the strong lensing region. And you can see from the weak lensing, you have those two low density substructures that are lighting with orange circles. And the one on the southwest is called S1. And when you look at the distribution of galaxies in S1, what you can, one hypothesis is that S1 is actually a large-scale filament aligned with the line of sight. And one explanation would be for C2 being a progenitor from S1 and being on its way to actually merge with C1 for first co-passage. So it hasn't merged yet. And that we know thanks to actually the X-ray observations that are showing us the gas dynamic within the cluster. Another thing that Buffalo is going to do, and that I'm super excited about, even though this is not my expertise at all, is actually another way to constrain the cluster evolution is by looking at the ICL, so this intra-cluster light. And so the intra-cluster light is made of stars that are not gravitationally bound to any of the cluster galaxies. And so it's believed to be a product of the galaxy interactions. And actually, in some clusters, it can reach up to 40% of the stellar mass in clusters. You can see on the right-hand side a simulation, a Sea Eagle cluster. You can see the stellar mass map at the top and the ICL map at the bottom. And the ICL actually is a unique tracer of cluster assembly over cosmic time. And it's been shown that it actually follows the dark matter distribution. So combining both can also give us clues on actually the dark matter itself. However, the limitation with ICL is that you need extremely high resolution imaging. So you need HST. And so far, ICL has only been observed in the inner core of clusters because HST time is so expensive that you don't have mosaics like we got for Buffalo for so many clusters. And so now with Buffalo, they're going to be able to study the ICL up to the virial radius. and then try to constrain the different mechanisms that are actually responsible for the ICL as a function of the distance to the cluster core. And finally, I'll go quickly on that, is the fact that you can also look at transients thanks to those observations, because we designed the observing period to actually be optimal for those. This is an example of Residing, as the supernova Residing, that was observed in a galaxy that is being lensed, triply lensed by one of the cluster, 1149. So that was for the Frontier Fields observations. And what is actually crazy about the supernova is the fact that it was observed. You have on the left-hand side in one of the image of the spiral galaxy, and one of the spiral arm of that galaxy was actually itself lensed by one cluster galaxy, meaning that the supernova exploded in this spiral arm, but got quadruply lensed thanks to that cluster galaxy. So we ended up with 4 images of that supernova. And then because you have 3 images of the same galaxy, you expect to see the supernova in the other 2 images also, except light is taking a different path. So you have a time delay between all 3 observations. But our mass models are able to measure those time delays. And at the time, we got all teams to predict the reappearance of the supernova in the 2 other images of the galaxy. And we all agreed that the first one appeared like between 10 and 15 years ago in the northern one, so the one that you can see on the left-hand side, and that actually the next one would appear at that time within a year from the observations in the central image of the spiral galaxy. And so what happened is that we asked for DDD time on HST to keep on observing that cluster. And the prediction for the reappearance at the time started between November 2015 and up to April 2016, depending on the team. So we kept on going back to 1149, and on the 30th of October, you can see here on the patches on the right-hand side, there was nothing. So we were all a bit scared of our mass models being absolutely terrible at measuring time delays. However, when we came back on the 11th of December, HST, we actually observed the new images, as you can see at the bottom, on the bottom stamp, so of the supernova. So that was actually pretty amazing, because our mass models are systematic limited, but we're still pretty good at predicting those. And that was actually the first time we were able to test all our mass modeling techniques in real time and not wait for billions of years until we know if we were right or wrong. And here is an example of a star that is actually being lensed and at a redshift of 1.5 in the same galaxy as Rev star. You can see it on the top left, you can see it on the top left. And so this star is extremely highly magnified because it's extremely close to what we call the critical line, which is where the high magnification region is. And what is amazing with this star is actually we managed, because we kept on going back to that cluster, and we managed to actually observe its one of its multiple images on the other side of the critical curve. Anyway, all of this to say that you have a lot of things to do from a very broad science. But Buffalo is an open collaboration, so if you have any idea you want to join, if you just want to know more, you can go to our website. Just drop us an email to Charles and I. You can follow us on Twitter, because that's the new thing, and Facebook. We try to update with like any press release, any results, and please do ask at the end of the talk. And now I'm going to quickly talk about one thing that I have at heart, which is using those clusters as cosmological probes. So if you remember what I said, you combine strong and weak lensing, and then multi-wavelength observations in order to look at the mass distribution and the dynamic of your cluster. So this is one cluster. In orange are all the dark matter mass peaks that were detected with the lensing analysis. And then you can see in blue the X-ray remnant cores, so the gas associated with those mass peak. What comes out of this analysis is that this cluster seems to be extremely complicated, with the core at the bottom, which is basically the frontier field of view. And so we have 8 dark matter substructures, and all of them are extremely massive, like 0.5 to 1.410 to the 14 solar masses. So all of those substructures are like clusters, smaller clusters, group-like structures, and we're pretty close to the cluster core. We're not up to far away where those filaments are like coming in. And so I tried to sketch the mass distribution and what was happening in this cluster, and I ended up with this, which is basically a huge mess. So we have like mergers with all the components, and we basically, you can't really conclude anything because it's so complex. You can't like draw the history of the cluster like I did with the other cluster that I showed earlier. And however, one thing that came up to my mind is, if you remember what I said about those substructures infilling the cluster, the number of them, the weight of them, being a dark matter probe, then I went to Johannes Schwinn, who was a master's student at the time in Durham, and asked him to look into the simulations to try to find a cluster that was similar to what we observed in Able 2744. So he looked into MXXL and found 70 clusters, the similar redshift that were as massive as Able 2744. However, when it came to the number of subclusters and groups in the surroundings, he could not find any clusters that were actually similar in terms of substructure distribution. So before claiming a conflict with the cosmological paradigm, lambda CDM, we highlighted a few limitations. First on the observational side, because lensing is giving you a projected mass distribution. So it sums up everything along the line of sight. So you have to make sure that your substructures are actually part of the cluster, and you can have contaminants by things that are behind the cluster or in front of the cluster. And then second, on the numerical aspect, the lack of resolution. So you're using the sub-hello finder algorithm. So they look at all the particles and they attribute all the particles to a substructure. And in really dense environment, this algorithm that was used in this case, I find, actually is lacking resolution. So it tends to give the particles to the more massive halo and miss on the smaller substructures. But then we got the particle data, because up to now we only had catalogs that were made from subfine. And with the particle data, we were more able to get something that was closer to our real observations. And so that's what you can see on the left-hand side is the mass map from the MXXL on one cluster. And you can actually see that you have those multiple substructures. And we ended up with finding not many clusters, but we got one in MXXL that had a mass distribution that was quite similar to Able 2744. So we did not declare any conflict with lambda CDM so far. Then I moved on to another cluster, which is at higher redshift. And I did exactly the same thing. So you can look at the mass distribution here with, like, again, in orange, the dark matter substructures, and in blue, the gas counterpart. And when I saw this, I found it quite similar to something we've just looked at, which was the mass distribution of Able 2744, which is at a lower redshift. So then I asked myself the question, can one be the progenitor of the other? And so I looked with my hands, basically trying to constrain this, and decompose the mass distribution in all of those clusters from the contribution from the core, from the galaxies, and those substructures. And that's what you can see on this plot here, which is the density as a function of the distance to the cluster core. And you can see in the substructure, which is the straight line, the peak due to those clumps that you could see on the mass map in orange. And between redshift 0.5 and 0.3, you can measure the infold distance analytically, and you expect the infold to be like roughly 2 megaparsec, which is basically what you observe here. And if you apply those to the case of this cluster at redshift 0.55, you expect it by the redshift of 0.3, which is the redshift of the initial cluster that I was showing, that most of the substructure will have passed their virial radius and will be actually at distances that are similar to where we observed them in the other cluster. So then we turned to numerical simulation. This time we went to hydro simulation, because like this we could look at the, take into account the impact of baryons, and we looked at the particle data, didn't make the same mistake as we did before, and we found a cluster that had a similar mass distribution that you can see here. We measured infold distances, and they were like roughly 2 megaparsecs. So that's good to know that analytical and numerical are agreeing with each other. And we measured a growth rate, and also a gas fraction, the gas fraction for all of those small substructures, which was between 1 and 5%. And what the main conclusion of this analysis was that, yes, such a cluster is the progenitor of at 0.55 to another cluster at 0.3. So we're looking at superclusters. They lie really at the limit of the lambda CDM paradigm. However, they still agree with the predictions from the simulations. One cool thing that we actually were able to measure here is like I said, the fraction of gas, because we had it from the observation and from the simulation, and we have a really good agreement. And yeah, so even if at the limit of lambda CDM, those cosmic beasts so far actually are not going against the idea of dark matter being cold. So I finally conclude by saying that multi-wavelength analysis are key. I think you got that, and if not, please remember just that of my talk, if anything else. There are tons of things, other things that you can do. I didn't have time to talk about all of them, but you can look at luminosity function at high redshift. You can use other type of cosmological tests, actually. You can look at large-scale structures. And I highlight the work from younger people that I'm closely working with, because without them, Buffalo wouldn't go as well. So it's Anna working on the strong and weak lensing analysis. The other, Anna Sebron from Israel, both of them are actually in charge of the mass modeling challenge for Buffalo. Then David Lagatuta, who is working on news follow-up of those clusters, and Guillaume Malher, who is also working on strong lensing and dark matter constraints. Finally, a quick highlight to show you basically the scale, and then I'll be done. So in here you can see the Frontier field of view, then the Buffalo field of view with the Hubble. But what's next after that? And also keep in mind that Buffalo is only 6 clusters. So statistically, it's better than 0, but it's still quite limited. So what is coming next is actually SuperBit. SuperBit is a balloon-borne telescope that will be launched next year from New Zealand, and it's gonna go for 3 months of observations. It has a wide field of view, pretty broad range in terms of wavelength. So 0.5 square degree. The advantage of balloon is that you get almost space-based resolution, but it's much cheaper than a Hubble, that you can guess. Here is just for the fun of it, some pictures for the engineering flights that we took in Palestine, Texas, and Timmins last year in Canada. And here are some images that we took in 2018 during the 2018 flight. And those are the last ones from last September, with the comet Borisov actually being in the field of view that one time. And I thank you very much for your attention.
Excellent, and we have lots of virtual claps as well, so awesome. So are there any questions? If you want to raise your hands or unmute your microphones. Yes, we have at least one question, so Kirsten, go ahead.
Let me see if I can, am I on? I'm unmuted, okay.
Yes, yes.
So when you said you had predictions you showed from the Buffalo survey for beyond redshift like 8 and 10, I could see on the plot you had even had redshift 6 and so on. Is that all photometric redshifts?
Yeah.
And what's the accuracy?
God, the number, can't remember. Can't remember which one we assume for this. If you give me a minute, I can check exactly.
It's really impressive data that you're getting.
Yeah, you're welcome to join, Kirsten.
Thank you.
Join Buffalo. We need Alma people, actually.
Let's talk.
Yes.
Okay, should we do another question while you're, so Kay, if you want to ask your question.
Yeah, hi. Thanks for the nice talk. You have this mass model. Can you say something a little bit more about what kind of dark matter you're using?
So okay. When I do my mass model, I don't use any dark matter candidate. It's just lensing that is giving me a mass distribution, and from that I subtract stars and gas. But so far, like the results that I showed you when I compared to numerical simulations, it's to cold dark matter simulations. But we now have in Durham runs with warm dark matter and different type of self-interacting dark matter from Sea Eagle and the Bahamas numerical suite. So we are actually going to use those now to get a perspective of different families of dark matter.
Okay, a quick one. What about the mass to light ratio compared to the, before Buffalo? Is there any big change?
I'm not sure I understand what.
Well, I assume all this cluster had calculated the mass to light ratio, right?
Yeah,
so
but
I was wondering what Buffalo has contributed.
So far, Buffalo has only one cluster that was complete. So end of observation is going to be of full. So those measurements haven't been done yet. We're working on the mass model of Able 370 at the moment. So there is no mass to light ratio so far. We're just working on optimizing the mass model.
Okay, thanks.
Okay, any other questions for anyone else? I'm not seeing any hands raised, so I think that's the end of the question.
She has a question.
Yep.
Sorry, I don't know how to raise my hand virtually. So thank you for this interesting talk. I just wanted to ask you about this new code, the hybrid lens tool.
Yeah.
See that it's on GitHub. Students working on lens tool and downloading it from the lens tool website. So is it also there, or is it a separate tool?
No. It's going to be a branch of lens tool. So far it hasn't been released because Anna is just cleaning up the code. She doesn't want to make her code straight away public because it's full of notes and silly things everywhere. But it will be released by within the next few months.
Great, thank you.
And it's just going to be a branch of LensTool, so it's going to be usable as LensTool is, just with a different command to start the code.
Nice, thank you.
But I'm happy to send you an email once that is done if you want.
Thank you.
Okay, great. If that is it for questions, then let's give another round of applause. And thank you very much for joining us today.
Thank you. And I'm checking that number and I'm sending it to you.
Thanks.
So there will be another seminar next week. I'm just waiting for the speaker to confirm. And the week after that, there will be a seminar on exoplanets. So look, I'll send emails around about that. Thank you for joining us today and have a good Wednesday. See you later. Bye-bye.